On to part C. In part C, we need to find the actual particular solution, which means that we're going to have to solve the differential equation dy over dx is equal to negative 2x over y. In order to do that, we can try our separation of variables technique, always a great technique. This is a proportion, so we can cross multiply. And we get y times dy equals negative 2x times dx. I have successfully separated my variables, everything with a y on one side, everything with an x on the other. The next step is for us to perform the integration. The integral of y with respect to y, that's our general power rule, and we get 1/2 y squared equals, same thing over here, the integral of negative 2x will be negative x squared plus c. Don't forget Charlie. I need to solve this for the particular solution, which means we're going to get y by itself. I'm going to multiply both sides by 2. Y squared will be equal to negative 2x squared plus 2c. You can remember that c is an arbitrary constant. 2 times c is still an arbitrary constant. That's our friend Super Charlie helping us out. This has to be true, subject to the condition f of 1 equals negative 1. So that means that the point 1, negative 1 must be on this curve. I will replace the y value with negative 1. I'll replace the x value with positive 1. We'll quickly solve that out. Get 1 equals negative 2 plus c. So c must be equal to 3. That's our constant. In order to finish off this problem, you'll have to use that c in the original equation. And we're going to get that y squared is equal to negative 2x squared plus 3. Depending on the statement of the problem, you might actually have to solve it for y. Or you might be able to stop. This one says find the particular solution, y equals f of x, which to me says they want me to find a function. So this would not count as a function. I think you would probably lose a point. In order to finish this off, we're going to solve it for y, which is going to involve taking a square root. We'll have the square root of negative 2x squared plus 3. Now the problem with the square root is it gives you two answers, the positive and the negative. And so let's stop and think about this. If I have a choice between the positive of the square root, negative 2x squared plus 3, and the negative of the square root of negative 2x squared plus 3, how do we decide? Is it this first one? Is it the second one? The decision will be made by considering your initial condition. I need to know which one of these functions will actually pass through the point 1, negative 1. If I replace the x with 1, 1 squared is 1 times negative 2 plus 3. If x equals 1, with this part, I'll get y equals positive 1. That is not the solution that I'm after. I have to eliminate this option. Let's make sure it does work over here. If x equals 1, then we get that y equals the negative of the square root, negative 2 times y squared plus 3. 1 squared times negative 2 plus 3. We do get negative the square root of 1, which is negative 1. Y equals negative the square root of negative 2x squared plus 3 is the solution, is the particular solution to this differential equation that satisfies our initial condition. Congratulations. You've just solved your first AP question involving slope fields and differential equations. We're going to move on to the next one, and I want to tell you, I think this next one is much more complicated. We're going to be doing some work with the cosine function. We're going to see a lot of algebraic manipulation as well as some trigonometry. All right, let's get started on this one. This, in my opinion, is a really rough slope field question. If you take a moment to look at the differential equation that we're going to be asked to solve in the course of this problem says dy over dx equals y minus 1 squared times the cosine of pi times x. This one is going to be a beast. In part A, we're going to be asked to generate a slope field. Of course, we can find a slope field. We're just going to plug points in. We can do that at the points that are indicated. In part B, we're told that there is a horizontal line with the equation y equals c that satisfies this differential equation, and we're going to be asked to find the value of c. That'll be a relatively easy question. Part C, we're going to be asked to find the particular solution to the differential equation subject to this condition f of 1 equals 0. This should sound very familiar to the last question. These are typical slope field questions. What makes this atypical is it's a more complicated differential equation than I've seen in some of the other exams. So let's leap into part A. In order to generate a slope field, I'm going to need to take the 9 points. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 points. We have negative 1, negative 1. We have the point negative 1, positive 1. We have 0, positive 1, 1, comma, positive 1. We have the point negative 1, 0, 0, 0, 1, 0. We have the point negative 1, negative 1. We have 0, negative 1. We have 1, negative 1. All 9 of those points will need to be plugged into your original derivative. We'll go through and actually determine the slope, and we'll generate our tangent lines. So we're going to do this one very carefully. Let's start with the first point. I'm going to evaluate my derivative at 1, comma 1. So I'm going to plug this in. 1 minus 1 squared times the cosine of pi times 1. This one actually is not so bad. 1 minus 1 is 0. 0 squared is 0. Regardless of what the cosine of pi is equal to, this whole product will be equal to 0. So at the point 1, 1, right up here, I'm going to draw in a tangent line that is horizontal. Okay, let's pick another point. If we want to find dy dx at 1, comma 0, well, let's do that. We evaluate it. Y minus 1 squared, 0 minus 1 squared, times the cosine of pi times 1. 0 minus 1 is negative 1. Negative 1 squared is 1. So we've got 1 times the cosine of pi. If you're not so confident with your trigonometry, maybe it's a little bit rusty. Quick refresher on the unit circle. For any angle theta, the point on the unit circle, the x comma y, if we're on the unit circle, the x-coordinate for that point represents the cosine of your angle. The y-coordinate represents the sine of your angle. So if I wanted to find the cosine of pi, pi would be over here at the point negative 1, comma 0. Cosine of pi is equal to negative 1. So at the end of the story, we have the derivative at 1, comma 0. So the slope of the tangent line will have a slope of negative 1. I'm going to go over to the point 1, comma 0. I'm going to draw in my tangent line. My tangent line will have a slope of negative 1. We'll do this for all of the remaining points. dy dx at 1, negative 1 is going to be equal to negative 1 minus 1 squared times the cosine of pi. Negative 1 minus 1 is negative 2. Negative 2 squared is 4. We have 4 times the cosine of pi. Cosine of pi, we've already done the work. We know that's negative 1. So I have a slope of negative 4. I need a line segment that decreases faster. Again, I want to leave no room for doubt. So not only will I draw it in so it's decreasing faster, I'm going to have a slope of negative 4 at that point. And then we're just going to repeat the process at the remaining 6 points. For the sake of time, I'm not going to work through all of them. I do want to call special attention to 2 of the points. The first point we selected was easy to determine the slope because the first factor, this y minus 1 squared, was equal to 0. it was 0 when the y value was equal to 1. We have two other points in this slope field, namely right here at 0, 1, and over here at -1, 1, where we'll have a tangent, a horizontal tangent for the exact same reason. Over here at the origin, we'll have a slope of +1. Where are my notes? Over here at -1, we will have a decreasing line. Over here at -1, -1, the line is decreasing even faster. And over here, it is increasing. The specific values, that's going to have a slope of +1, slope of -1. This should come out with a slope of -4. And this one over here should have a slope equal to +4. That's part A. I didn't want to belabor the point and plug all 9 of those in. I did want to call special attention, though, to these 2 points. These are ones that you can get relatively quickly. Everything else is just plug the numbers in, evaluate the derivative, and go from there. So let's move on to Part B. All right, so here we are with Part B. In Part B, we're told that there is a horizontal line that has the equation y equals c that satisfies this initial differential equation. Our goal is to find the specific value of c. Well, let's look at our derivative equation. We're told that dy dx, the derivative, is equal to y minus 1 squared times your cosine of pi times x. Well, the derivative of y, if y is a constant, then we know that the derivative of a constant is equal to 0. So our differential equation becomes 0 equals, instead of y minus 1 squared, c minus 1 squared times the cosine of pi times x. We're looking for the specific value of c that will make this product equal to 0 always. Well, one of the things we would have done back in Algebra 2 and in pre-calculus, if the product of these two factors is equal to 0, then it means that one of those factors is equal to 0. C minus 1 squared equals 0, or the cosine of pi times x equals 0. This equation over here doesn't even have c in it. I'm looking for the value of c that will always make my original differential equation equal to 0. That happens over in this branch. If c minus 1 squared is equal to 0, c minus 1 must be equal to 0, c is equal to 1. That is actually the value that we were after. That's all the work that is involved in solving Part B. All right, here comes Part C. This one is going to be a little heavy with the integration trickery, so you definitely want to pay attention to this. There are 6 points out of 9 associated with solving this problem, and along the way I'll try to point out where the points are. So I want to find the particular solution to this differential equation subject to the condition f of 1 equals 0. I'm going to try to start all the way over here because we are going to fill the board with our calculus. dy over dx is equal to y minus 1 squared times your cosine of pi times x. Our favorite trick so far has been separation of variables. I see I have a factor over here that has y in it. Fortunately, no y terms over here. This factor has an x in it. Fortunately, no x over here. We have the dx in the denominator. If I multiply both sides of my equation by dx, we now get dy equals y minus 1 squared cosine of pi times x dx. I can divide both sides by y minus 1 squared to yield dy over y minus 1 squared is equal to the cosine of pi x dx. I want to integrate both sides. First point is awarded to you when you separate your variables. Points 2 and 3 are going to come in from doing an integral. The integral of dy over y minus 1 squared, you can do this using your integration by substitution. You can do some trickery. The integral of dy over y minus 1 squared is going to be negative 1 over y minus 1. The integral of the cosine of pi x will be equal to the sine of pi x times 1 over pi, and then plus c. I know I went a little fast there with the integration, but I would encourage you to do integration by substitution. You're going to let u equal pi times x. The derivative of u will be pi times dx. You'll need to multiply by 1 over pi to get this into integral-ready form using substitution. You could do integration by substitution on the left as well. You could let u equal y minus 1, so the derivative of u is equal to dy. You replace this, replace your integral and then solve it using your general power rule. It's either 2 points or 3 points available to you for reaching this step. You get 1 point for integrating the expression on the left to give you this. You get 1 point for integrating the expression on the right to give you this expression, and then in some cases you get a 3rd point just for remembering to put your constant of integration. The remaining points are going to come to us by solving the differential equation. We want to solve this for y. We're going to evaluate that at the point 1, 0. We need to do that quickly. So here we go. Negative 1 over y minus 1. In order to get the y minus 1 out of the denominator, I could cross multiply if that's something that you'd like to do. We can absolutely go through and do that. Or, one of my favorite things to do is you can take the reciprocal on both sides. And if I take the reciprocal of this fraction, I'll get y minus 1 over negative 1 is equal to 1 over 1 divided by pi sine of pi times x plus c. I want to solve this equation for y. In order to do that, I will multiply both sides by negative 1, canceling out this negative. I'll then add 1 to both sides, and what we will get is that y is equal to negative 1 divided by 1 over pi sine pi x plus c, c being in the denominator because we've done the reciprocal, and then plus 1. You pick up another point by solving it for y. Okay. So we've made it to this point. We've solved the equation for y. I need to evaluate the function at the point 1, 0. That's my x, that's the y. So I have 0 is equal to negative 1 divided by 1 over pi sine pi times 1 is just pi plus c, and then plus 1. This is definitely an algebra issue. The sine of pi, we know that to be 0. 1 divided by pi times 0, that is all 0. 0 equals negative 1 divided by c plus 1. I can subtract 1 from both sides. I can multiply both sides by c. Negative c is equal to negative 1, so c must be equal to 1. To wrap things up, all I need to do is take this specific value of c, plug it back in, and so y will be equal to negative 1 divided by 1 over pi sine pi x plus 1, and then plus 1 to the entire fraction. That, my friends, is your particular solution to this differential equation, subject to that initial condition. That is the 6th point in this problem. There's a lot of places to make mistakes. The AP folks are really generous as long as you are providing them good calculus. If you make a mistake on one side of the integral, but you know what to do, keep going. Move through this problem. Move as far as you can. If you make a mistake early on, just keep going, and good luck to everyone. Yes!